Welcome everyone from lunch. I'm Wesley Kerr. I lead tech research at Riot Games. I'm here today to talk about how we're using large-scale deep learning to augment our production RL workloads. Quick run through of the agenda. First, we're going to talk a little bit about who Riot Games is. We'll dive into one specific game, Teamfight Tactics, frame the reinforcement learning problem, and then how we're using supervised learning, and then conclude with some remarks. So Riot Games is the developer and publisher of League of Legends. Over the past few years, we've expanded our portfolio. We've included new games, so we have League of Legends Wild Rift, which is our mobile version of League of Legends. We have Teamfight Tactics, which is Riot's take on the auto battler genre, and Valorant, which is our version of a tactical first-person shooter, and then Legends Runeterra, which is our trading card game. Today's talk is primarily focused on Teamfight Tactics. As I mentioned, Teamfight Tactics is Riot's take on the auto battler genre. It is set in the League of Legends universe with our champions, items, and monsters. Teamfight Tactics is a relatively new game for Riot, and therefore also a relatively new game to balance and design around. So Teamfight Tactics, play takes place in rounds. So every round you are building up your board. Your board consists of champions that you buy and place on your board. And rounds compete, you get a random selection of champions that you start from, down here on the bottom of your screen. You have gold. Every champion costs gold. Every round you get more gold. It's an 8-person game, and your job is to survive longer than all the others. Every round your board wins, you do damage to your opponent. Every round you lose, your opponent does damage to you. There are a bunch of different champions to choose from. Every champion costs different amounts of gold. Their abilities sort of scale with their price in gold. You get gold again every round, and you can save up to get better champions. You get 3 of the same champions. That champion levels up to level 2. Level 2 champions have more abilities, are stronger. You get 3 level 2s, and you now have a level 3 champion. Again, leveling them up, making them more powerful for your board. Throughout the game, you also get items. So items drop in PvE rounds and other places. Those items you can attach to a champion. That gives the champion better stats. They can do more damage, take more damage. You can combine items to make more powerful items. And here we have a needlessly large rod and a recurve bow combining to create Ginsu Rageblade, which gives your attacker more damage, attack speed that stacks. And so you can place that on your favorite Yordle, here Tristana, and Tristana will do that much more damage in each battle. Champions also have classes and origins. So here we have Ezreal, who is a Tempest Swiftshot, and Ashe, who is a Jade Dragonmancer Swiftshot. If you have 2 champions that, when placed on the board with similar classes or origins, or with the same class origins, you can get a synergy, which will also give you additional bonus stats for your board. Again, making that board stronger in the next battle so that you can win and continue to outlive your opponents. And so here we have 2 swift shots on the board. We gain the synergy swift shot, which gives us plus 10% attack speed. Okay, so this is a round actually playing out. So champions, you do not control them once they're on your board. They fight each other on their own. Here you can see I'm going to lose, but at the end of it, I'll take damage, and don't pay attention too much to my synergies here. I was way more worried about getting a good video than I was about winning this game. And so that's why I ended up losing. Probably not the only reason, but. And so here, towards the end, you'll see I'm going to lose. Damage is done to me. My health drops lower. And again, over time, you try to survive and outlast your opponents. So we spent a lot of time. That's TFT in a very short nutshell. You're still lots more to learn, lots more depth there to learn as you go to become a master of strategy in Teamfight Tactics. And I bring that all up now to really set up, it's important to understand the game that we're playing in order to understand how we're going to use reinforcement learning to solve it. So the reinforcement learning problem that we're looking at is we want to build an AI that learns to play TFT at the highest levels. It's not there just to stomp on our opponents. We actually want to learn so that we can do things like metagame balance. We can unlock other player features that are very valuable for our players. There's been incredible progress for reinforcement learning in games over the past few years, from the early papers where we had human-level achievements in Atari, to later work by DeepMind and OpenAI, where they played top-tier matches against StarCraft and Dota 2 teams, respectively. We hope to stand on the shoulders of these giants and make our AI that learns to play the games in similar ways that they did. But we're going to take it to the next step, which is further, which is how do we bring that value of an agent that plays really well back to features that will impact our players and make our games better. And we've begun to improve those game experiences using deep reinforcement learning. Now, I'm not going to dive deep into those successes in this talk. In fact, I'm going to point you to an excellent talk by Ben Casper sitting right over there at the AnyScale RL Summit, where he talks about how we've begun to improve those experiences using reinforcement learning. Instead, here I'm going to focus on, at the end of the talk, he talks about how we are been doing more with TFT. And we're going to dive into how we've been doing that with TFT. So in 2020, the team had the audacious goal to build AI that plays at the highest level, but we encountered some challenges along the way. So TFT launched in 2019. This new genre, auto battlers, came into existence then. And very quickly, Riot wanted to create our experience of an auto battler set in our world with our players and champions. And so the team moved extremely fast to launch Teamfight Tactics. And along the way, they didn't really stop and say, hey, you know what, maybe later we're going to want to hook up an AI to this and learn to play. So the integration doesn't exist for us to work with the game servers. TFT constantly evolves. Part of the fun of this game is solving the puzzle, figuring out what best champions are, what the best synergies are, what items to put on who. And so to keep that fresh, we launch new sets where we change the mechanics, we change the dynamics, and really sort of keep players excited to come back and play. So that means our AI is going to need to learn on something that's constantly evolving over time. And then lastly, Riot Games' mission is to be the most player-focused game company in the world. And we can't achieve that mission unless we're focused on delivering as much player value as possible. This can make it really difficult to tackle multi-year projects like build an agent that learns to play TFT when you have to offset of what player value is going to come out of it. And so because of these challenges, we actually went out and built our own version of TFT. So here's the programmer art for our game. It turns out that building a lot of the metagame, the buying, the selling, the putting items on, placing items on your board is pretty easy to code. So we programmed it up in Python pretty quickly. Here you can see the same hexagonal board that you saw before. You have your bench, you have your buy menu, and then the battles are taking place over on the right. Now, one thing that I'm not going to bury the lead on this is that it turns out that the hardest part of building that game is actually programming all the champion abilities for those battles. So you saw the champions running around attacking each other. That's the complex part. And we're scientists and researchers, and we don't want to spend our time writing games. We have game teams to do that. And so what we set out to do was, could we take a supervised learning algorithm that could predict outcomes for the battle? That way we don't actually have to train up or write all the code for the individual agents. And so what that looks like is actually here. So here you have two boards. We'll call them home and away for simplicity. The champions are varying levels. So there are some level 3 champions, some level 2 champions. They have different synergies that are currently active given the board. And then they're going to fight. And we have that data. And the damage of this particular outcome is -12. So the home team took 12 damage. Now on the right, what you actually see is the x-axis represents all the different damages that are possible. And the y-axis is the probability of that damage occurring, given this specific board. And so what's really at play here is that outcomes are not deterministic. So depending on how the agent decided to target, how they decided to move in that round, you can get very wildly different outcomes. And so here, we need a model that can actually not just predict a single scalar value. We need a distribution over all the possible values. Luckily for us, we've had lots and lots of people playing our game. We have lots of these boards to draw from, and there's just a whole lot of information in all of these. There's different champions, there's different items, there are different star levels. Some boards have very few champions, so you have a 3-star down here against another 3-star, and then one extra Malphite. That's really a late game comp, but someone, for whatever reason, these two players were kind of goofing off. And some of you may be sitting there going, I've got a bad feeling about this, because what we have is a bunch of player data that we're going to build a supervised learning model on. We're going to use that to feed an RL loop and train on that. And so there's this problem of distributional shift or domain adaptation or domain adaptation that we have to worry about in this case. We are 100% certain that our RL agent will encounter areas of the state space that our model has not been trained on. because the RL agent is playing more randomly than than our players are. Our players are following very specific strategies and are doing very specific things. And so this distributional shift is going to be a challenge for us. And it was a big concern expressed by the team of like, how are we going to encounter this and get agents that we train on this supervised learning policy that are going to work in the real game. And so we took our player data, and that represents the majority of the training data that we have. So our players are really great in that they play lots of games, we get lots of boards, we get lots of data. Then we worked with the game team to create a combat simulator. So the simulator here is actually able to take 2 boards, simulate the outcome, and we can then add that data to augment our training data set. And so what we do is we grab a bunch of data, just randomly generate boards that we're more likely to encounter in the RL space, and we send them through the combat simulator. Now the simulator is too slow to hook into the RL loop. It takes about 30 seconds to do one battle. So you imagine if you're trying to build an RL training algorithm on that, you're going to be waiting days. And so we do that with the random, and then we also augment player data. So imagine here is that players may always play tanky champions in the front and soft, squishy champions in the back. We will randomize where they play just so that we have better training data to train our supervised learning model. The other thing that we wanted to tackle was many different model architectures. So here we want to quickly iterate on different ones, find the best one that is going to lead to the best possible outcome for our reinforcement learning. And so here we have a pretty standard ML training loop. We have a bunch of battles. We transform the data into the neural network input. We run our train loop, and then we get out a model. The types of models that we want to run through this, we could have just a simple feed-forward neural network. So here are the inputs. We've thrown away the position information. We've thrown away the item information. And in fact, we're just sending what champions you have on the board. We look at this as our baseline. So this is the floor of how well we can do predicting the damage probabilities for those battles. If we start in bringing in more additional information, so here we have positional information coming in. Now we can leverage convolutions to sort of better understand how one player's position affects, one champion's position affects another champion. And we get a better model out of this architecture. And then lastly, we can go full transformers on it and bring in all the champion information. Position now is encoded as an integer. And the model can learn to attend to where it wants to and pay attention to the champion matchups that are important. Now, one key thing on all 3 of these is if you notice, all of them have very different inputs. And that's going to be a theme that we talk a little bit more about as we go forward. So here we have, I'm going to focus on the first part of that training loop, which is really just have battles in, transform it into neural network input. And what that looks like for us is we have a bunch of battles in sort of a standard JSON format. We run it through a small bit of Python to encode that battle into the correct neural network input. So this code is associated with each architecture. Each architecture knows how to take a battle and turn it into the stuff that it needs for training. And the output is then a dictionary of inputs to NumPy arrays. So a very simple function, but a very important one that we can use to feed into these large-scale distributed systems. So we set out first with the Spark workflow. And here we have 2 jobs. The first job will read the battles in, run the transform step, which is actually just doing that map function I alluded to earlier, and it's going to write out TF records files. So we are a TensorFlow shop. We use TF records and TF data in order to keep the GPU humming. This write is done in Spark, where we're basically going right to TF record, and it's inferring the schema along the way. So that write schema is going to be important. We have a second job who reads these TF records using TF data, runs it through the standard Keras training loop, and will write out the Keras model, then solving our problem. Now this read loop, you have to define the schema that you're going to read so that it can parse the TF record file and generate the right data set to train on. And what we found was quite often the inference process in Spark would pick the wrong type for some data being written. And so your schema for write did not match up with your schema from read. The errors you get of that are pretty opaque. We lost a lot of time debugging these things, and it really slowed down our ability to iterate on these different model architectures. So we built a Ray workflow that leveraged Ray data, Ray train, and Ray tune. And here we're reading the battle. We're doing the transform as part of Ray data. Then we do the training loop as part of ray train, and it's going to write out that same model. Now, nothing's ever free. Here we recognize that the other problem we had in the previous workflow is that we also serialize a lot of different data sets. Now you have a governance problem where you need to go back and clean them all up. But you could reuse the same data sets if it was valuable. In the ray case, we don't serialize out all those data sets, which means we may need to recompute that in code battle every time. That's a trade-off that I'm willing to make because I'm optimizing for scientist iteration time, not how much compute that we're solving or not doing. A little bit of the ray workflow itself. So here's the skeleton of the source code for the training file. We have basically 4 functions we'll go through. Our encode battle, here we have a model registry which keeps track of all of our architectures. Those architectures know how to parse battles and generate the right neural network inputs. So this encode battle function just allows us to do that as part of a map function. The data set here is we're just reading JSON, compressed JSON. We're repartitioning. It turns out the data set that we're running, when it's fully hydrated, it's about 2 terabytes. And so here we want to split it up into many different smaller batches so that we can run the map function far more efficiently. We do that for both training data and validation data and return that back. The train function is the biggest function, although it's not there's not a lot of complexity in here. And I'm really excited for the ray air additions to simplify this even further. So here we have the same model registry. We need to load the model. We need to prepare it for training. We check to see if there's any checkpoints out there. If they are, we override the weights with the previous checkpoint. And then we gather our data. For validation, we're only going to randomize once at the beginning. We're going to convert it to TF records. And here, this 2 TF records, which was causing us problem before with the schemas, is much easier because it's fully encapsulated inside that model. So here we have the output signature. The model knows what it's going to output. It also knows what input features it's interested in and their types. And so we can define that one place. It's all together. These architectures are all self-contained. Then we start the for loop over our epochs. So this is just our standard training loop, hard-coded 100 for fun. We randomize our training data, convert the training data to TF records as well, and then just call the regular Keras fit. After each epoch, we save a checkpoint and report how well we've done on the validation data. The tune function is our orchestrator. So its job is to make sure all the data is loaded and ready. We create the ray train trainer. Again, we said we're TensorFlow. We're using GPUs in this case. And then we call tune run, and it orchestrates everything for us. So some of the benefits we get with Ray is our iteration time is greatly reduced. We can make changes without needing to rematerialize those TF records data sets. And this is sort of a standard data science loop where you have the problem definition, your ETL feature extraction, some training, and then once you're happy with your model, you put it into deployment. The red line there is really for us to iterate much more quickly. As you saw, we have different architectures. We have different things there, and I really want that loop to be as tight and as quick as possible. Going from laptop to distributed requires less steps. So here, I can spin up a cluster in any scale. We don't manage our own infrastructure. Again, we're a small team of scientists. I want scientists to focus on the research. I don't want them worried about spinning up infrastructure, tearing it down, and all of those things. So we leverage any scale to do that. Going from our laptop to the cluster is quite easy and quite fast. And then going from single GPU to multiple GPU, as we'll see some of these training later in some of the slides, you'll see how long it takes to train. We're at days now for like multiple epochs of some of the transformer work. And so the plan here is we want to be able to go quickly to multiple GPUs and bring that down and make iteration time faster there too. And then lastly, we get integration with RayTune so we can do hyperparameter searches and find the best possible parameters for that model so that we can really do our reinforcement learning on the best model possible. So I set up an experiment. This is not very scientific, but it at least, again, here I'm optimizing for our scientists' ability to iterate. So if Ray is in the ballpark of Spark, that's a win because we don't have to materialize all the data sets. We don't have the additional debugging steps from the TF records. And so what I did was just generated multiple data sets from 1 million to 100 million battles. We split, you'll see reported splitting into transform time, training time. And then we reported both our Spark time and our Ray time to do this. Training was done on an NVIDIA T4 GPU and Cascade Lake CPUs. Again, our infrastructure, we don't want to do it, so I hand off Spark provisioning to Databricks, Ray cluster provisioning to Anyscale, and let them worry about optimizing all of that for me. All right, so this graph highlights some of the training. So one row here is a single model. This model is our feed-forward network. The 4 different graphs are different data set sizes. So we have 1 million on the left and 100 million on the right. And then we have for each plot, there's this timing it took in minutes for Spark and the timing it took in minutes for Ray. What we can see, a couple things, and then blue is transform time and the red is training time. What we can see on the data set size from the biggest data set is that Ray is actually performing faster than Spark. Again, not terribly scientific because I didn't actually do multiple runs to get some confidence intervals around that. But what I wanted to see is, are we in the same ballpark? And on the large data sets, Ray is doing better. On the smaller data sets, it's hit or miss, and Spark tends to be a little faster. As we make a more complex model, so here we have our convolutional model. The charts look very similar, but they are different subtly. And again, we see the same pattern where on the larger data sets, Ray is doing better for us. On smaller data sets, they're at least very comparable. And then lastly, our transformer, I mentioned, takes much longer. Here, all of our time is spent training. I want to call out that we have not engaged with our machine learning engineers yet to optimize this. This is scientist code, scientist iteration code. So I think there are tons of room for improvement there. But the key thing is that our performance and our ability to iterate with one job versus 2 is the same. So the takeaways, Ray allows us faster iteration on deep learning architectures at our scale. Going from laptop to distributed required less steps for us. Our code was more concise. We could pull a lot more together and really button it up in nice ways. And the speed is on par with what we got out of Spark and TF data. And then finally, using Ray unlocks these other features that are going to be valuable for us, as we mentioned, one Ray Tune and eventually Ray Serve. Now, some of you may be going back to the original title of this talk and had come in expecting to hear about how we're bootstrapping RL with supervised learning through different mechanisms of behavior cloning or imitation learning or these other techniques to make our RL better. And may feel a little hoodwinked or bamboozled, and I apologize for that. That wasn't the purpose. But I do want to just sort of walk through why this was valuable. So the team set out to do deep reinforcement learning for TFT. That was the balloon that we were after and we were looking to hug. Along the way, we ran into some challenges. So we did not have game server access. And so we had to find a way around that. So we built a custom game. And again, that felt pretty good. But then we had to code every champion's ability, again, setting us back. And so it was like, OK, now let's bring in a deep supervised learning model here. And then we started using Spark, and we hit other debugging challenges that slowed down our ability to iterate. And then we brought in Ray and sort of simplified that part of the training workload. So we're in a good spot here. And so I think the key takeaways for me here is that training AI, or deep reinforcement learning for TFT, is hard. It's a multi-year project. And we believe the way we've set this up, learning to play this game where we model the outcomes will transfer to the full game of TFT. Now, even if it doesn't transfer, we are able to work in parallel with the game team. So we're able to make progress on this really hard problem without impacting the team's roadmap, thereby allowing us to show the value of a good model at this game and what it's capable of, as well as make progress on how we would model the state, model the action, model all the different things in order to solve this game, so that when the game team does come and say, we're ready for this, let's do it on the real game, we're ready and well ahead of the game there. And I think the last takeaway is really that this path where we have this custom game that transfer over allowed us to move very quickly and make progress on hard reinforcement learning problems. And so with that, I thank you for your time, and I think we have time for 1 or 2 questions.
Thank you. All right, if we have questions for Wes, I'll run over and give you the mic.
Yeah, in your performance plot with Spark and Ray, did you also make sure that the errors, the training accuracy was same in both the cases, or?
Oh, yeah. So it's a good question, and yeah, the training, end result is performance on par with each other. I mean, it's not identical because of the same gradient pass, but they reach the same performance.
Right. Okay. And one other question was, so you set out to train an RL agent, but you ended up training a supervised learning agent that predicts the damage. Is that the cusp of it?
Well, no, the RL, we do RL at the core. So we are playing our custom game.
Yeah.
And the supervised learning is all about being able to circumvent or sidestep the real gameplay mechanics so that we can make progress on the RL loop.
Okay, and the goal of RL agent is to find strategies?
It's to play the game at top tier levels. When you build an RL agent to play at that level, you can then leverage that agent in other ways. So we can look at it for metagame balance. Are there strategies that are degenerate and that we need to balance for? Is the meta interesting so that players want to actually play the game? So there's a whole lot of those questions we can answer with it. We can also dumb it down and let it play against players so that there's an easier onboarding experience. We can also leverage it to do coaching. So you have an agent that now knows how to play the game at the highest levels. You can actually ask it what they should have done at this step instead of what they did, and then you could use that as a coaching moment.
Right. Yeah. Thanks.
Mm-hmm.
Hi. So I wanted to ask the three models that you were talking about. How good, or what's the trade-off between the three of them, the fully connected network versus the transformer, and how well do they perform, like approximately relative to the true simulator?
They get upwards of, so we have different, as I mentioned, it's learning a distribution. And so measuring our losses on that have been fun and a challenge. And so it's doing well enough that we can make forward progress on the RL task. So bad would look like it just abusing the system and not learning good strategies. The things that are coming out of RL are good. And therefore we believe that the combat simulator is there. And like each jump from like, so the baseline is like in the 70% accuracy, and then we added the convolutions and got to like 75, and then the transformers bring us up over 80. But the accuracy again is kind of tricky to measure, but that kind of gives you an idea of where we're at. There's still room to go, but yeah, we're doing pretty well.
And one other quick question. You mentioned that the TFT game itself is, continuously changing and being developed. So how do you incorporate that into training your model, whichever of the three you're using? Are you retraining from scratch every time you have a major change, or are you planning to do some sort of lifelong or continual learning?
The plan is more lifelong learning. Okay. So we've had success with other games where we're able to adapt to a new set by just sort of relaxing our learning rate at the beginning and sort of continuing from where we left off and give it several 100,000 more games to sort of figure out new sets. That's our plan. If it doesn't work, then we'll adapt and figure out something else. Trying to avoid going from scratch every time and really simplify our cycles.
So how are you guys encoding interactions between players within rounds, like adding items, or is all your data just from the initial board state?
For the supervised learning, it's those boards. So the items are already on there. From the RL game, there are different phases of the game that we've sort of built our game to contain. So before the battle phase, there is a round where the actions that are available are put items on champions, and you can choose, the AI can choose to do those actions.
Okay, I understand there are some mechanics like in previous sets or this set where you can actually take action in the middle of fights, right? So are you encoding every time step a user does something?
So in those cases, it's rare. I think that set will break this model, or those types of sets will, and we'll need to adapt for that and leverage a different representation. But for now, the sets that we've been using for this one have not had those mechanics in them, so we haven't had to worry about them.
For TFT, especially at the highest level, you typically have players that look at the other players' boards
Yep.
so that you can counter them and stuff like that. Does that also get encoded to the inputs today, or is that?
It's encoded into the RL side. So we've done it in different ways, trying to respect a player's ability to jump around to the different boards and how much they can take in. And so, yeah, we are offering up at least counts and different things for the agent to reason about what's likely to be on the other team's board.
All right, that's all the time we have questions for now. If you have more and if Wes has time, feel free to come ask him. But yeah, thanks again, Wes.
Yep. Thank you.